Okay, so I just want to give you a little bit of overview of where we're going today, with a few housekeeping items. So our first session this morning will be a session on topological photonics. I think over the last, especially yesterday, I think a number of the speakers kind of hinted at this notion that a lot of these ideas that we've used to describe condensed matter systems with electrons, a lot of that physics can be essentially mapped onto photonic systems. And so Boubacar and Mohammed are going to talk about that area of science today, which is actually insanely cool. Our second session today will be on quantum sensing with Ben Laurie and Professor Ashuka Joy from Berkeley. We'll talk about kind of practical implementations for quantum sensing, kind of where that activity is going. We'll have a panel after lunch on just the investment landscape, the VC landscape for quantum activities in general. That'll be actually run by Moses Isom, and we'll have some folks from Atlantic Quantum, and Misha yesterday actually mentioned those guys, right? Yeah, because he's actually part of that company. After that, we will have actually I skipped over Sean. So we'll have Sean Jones come and speak to you. Sean is actually a newly minted director of Argonne National Laboratories. And I thought it would be really interesting to listen to his career trajectory, because he started out as an HBCU assistant professor. And he's kind of walked through that entire realm of science policy space. And so I think he's a really interesting guy, generated specifically by his career path. And then we will close with kind of two discussions. The first one will be a kind of a discussion on resources that are available kind of across the national infrastructure. I'll talk a little bit about what's available through the National Nanotechnology Coordinated Infrastructure. Ken Evans-Littlerot will talk a little about what's available kind of through DOE laboratories. And Bill Ratcliffe will talk quite a bit about what's going on at NIST, and just kind of give you a flavor of what kind of work is being done and what kind of opportunities there are available for folks to do work. And then after that, I had kind of left that space between that session and the dinner fairly open. And I think what I'd like to do is I'd like to create a couple of breakout sessions so folks could ask questions, right? So I thought of getting together a group of young faculty just to talk about their experience and how they're navigating their academic paths, and then do exactly the same thing with folks in industry and in the national labs. And again, that's kind of an open thought about how we can do it. I'm willing to explore we have quite a bit of flexibility there, and I want to make it flexible enough so that folks get an opportunity to ask their questions. So I'm no longer panic-stricken because Boubacar is here. It's okay, I'm just going through some of our bookkeeping stuff. You're perfect. And then last but not least, I think I wanted to mention that I don't see Linda, I think the conference survey is going to get pushed out over the app today. Absolutely make sure you fill out the conference survey. Keep in mind, I'm going to have to go back and beg the NSF for more money, and the more data I have, the easier that is to do. So it's really, really important that you guys fill out the survey. I think also Damien was going to put in a poll for folks about yesterday's posters. And so I think the way he's going to probably structure it, he's probably going to want you to say, which were your most memorable, what your top three were. And oh, it's already gone out? Great, excellent. Yeah, so I'm old. I don't do app things that well, so I apologize. And then last but not least, I'll let you know what happens with the breakout rooms. I tried to get breakout rooms around near where our offices are, and I think those rooms are occupied, but I'll see if I can get people to switch up. But there's a lecture hall right down the hall from here. And so I think I might try to get physics to let us use that space. That's another one of their precious rooms. And so we'll see whether or not they were still in favor with the physics department after the last couple of days in terms of us letting them use their space. I think their spaces are open. I don't, because today I think maybe Misha mentioned yesterday we're opening our new a newly minted quantum engineering center. Actually, I don't remember who paid to have their name on it. So it was actually recently given quite a hefty sum to name the new building. And it's not a new building; it's a revamped old building. But that's opening today, and so they're hosting those folks today. And so actually we'll probably have a more of an intimate setting a little bit today because we'll have probably fewer of the Harvard Quantum Initiative students in our meeting today, in part because of that. And so unless there are any questions of me about kind of logistics for the next day, I'm going to just introduce Boubacar, and we can go ahead and get started. And why don't you come up and set up, Boubacar? Excellent. So as I mentioned, I'm going to introduce our first speaker this morning. Will be Professor Boubacar Kante, who is actually I have to put my glasses on because I'm old and I can't see anything anymore, who's the inaugural Channing Hu Endowed Chair at the University of California, Berkeley. And as I mentioned, Boubacar and Mohammed are really at the forefront of this really new paradigm of thinking about how to optimize our ability to control and manipulate photonic systems. And so I'll step out of the way and let Boubacar go ahead.
Great. Good morning, everyone. Thank you for having me here. Thank you, Bill. Amazing opportunity. So today I'm Boubacar Kante from Berkeley X, and I would like to tell you about some of the recent work we did, in particular on what we call scale-invariant lasers. So usually before going to the details of my talk, I like to give a quick overview of what we do in the group. So we, can I connect this? Yes, with a USB, that will be better. So we, a couple of years ago, so Mohammed will tell you more about topological photonics afterwards. So we proposed this idea of topological lasers, basically simply implementing the quantum Hall effect for photons. So we use 3-5 semiconductors that were on an heterostructured magnetic material, yttrium iron garnet. And when you apply magnetic field, light can circulate in one direction between two mirrors that are topologically distinct. And what is interesting is that you use the quantum Hall effect at optical frequencies. We know magnetism is weak at optical frequencies, so that was quite a surprise. And it is a laser that is basically intrinsically isolated. So I see you, you see me, because the environment between us is reciprocal. Light goes both ways. So if the environment was not reciprocal, I will see you, but not the other way. Okay, so here, light at the interface between these two photonic crystals that are basically two mirrors, two band gaps, light goes one way. And that is really important in photonics integration because when light propagates on chip, as soon as it meets another component, a discontinuity is usually reflected back to the source. And this is not good. It creates noise, inject noise back to the cavity, etc. So here you have an external magnetic field. And what is also interesting is that the actual interface here can be of any shape. So that is the manifestation of the robustness of topology. So that was very interesting. And we can also switch light on chip directly with an external magnetic field. So it was a surprise, and they selected it as one of the top 10 discoveries in physics in 2017. So we also work on singularities of open systems, known as exceptional points. Those are just singularity where you have two eigenvectors of the space that coalesce. So those singularities are typically implemented using what people call parity times symmetry. Very simple, you just distribute loss and gain in space, following some symmetries, and these singularities come for free. So we have explained that you can actually implement them in passive systems using polaritons, plasmons here. And why is that interesting? Is that polariton actually shrink the wavelength of light, right, to polaritonic wavelength. And if you want to do sensing, that new wavelength match the length scale of biological analytes. So you can do biosensing. So in this particular case, so we sense IgG, which is the most common immunoglobulin in the human blood. And we actually hold the record for sensing IgG with plasmons. And we have actually improved the previous record by more than 2 orders of magnitude. So we also proposed and demonstrated the first bond state in continuum laser. And we have shown in this work that these bound state in a continuum actually are the best if you like to make a laser compact and efficient. So it's basically a photonic crystal laser, but if you make photonic crystal, usually you need to make the surface large enough in order to have a quality factor of modes that is good enough to laser. So usually when you shrink the size, so when the first photonic crystal were demonstrated, I was still a baby, but we have shown that actually there is a class of photonic crystal that can enable compact and efficient lasers via these singularities. So continuing on this idea of topology, we have also shown that if you construct these topological edge states, so you can just think of the interface as being one being a donut and the other one being an orange. The orange has 0 hole and the donut has 1 hole. So if you alternate these interfaces, you have a donut here, an orange, so you have an interface, another donut, orange. You can do that as many times as you want. So it just depends on how patient your students are. So, and if you actually make the interface so that it is circular, so when light goes around the closed contour, it has angular momentum. And this angular momentum actually can directly be beamed out of the chip if the edge state is designed to be above the light cone. And so what is interesting, if you want to create light with orbital angular momentum, usually you buy a phase plate at Tor Labs or whatever. And this phase plate will give you an OM of 1, 2, not 200 or 1,000. So if you want that, it's very expensive because the resolution needed to manufacture these phase plate with high topological charge is, the resolution is, complex to get. So here, so it's very simple. For the same photonic structure, you don't need to change anything in resolution. The topological charge is simply given by the number of wavelengths around the perimeter of the ring. So I can beam out any orbital angular momentum that you want. So here we have, in the same interface, 3 OEM that are multiplexed. So this is also, I can say, the largest OEM directly emitted by laser, because this is again done on a 3-5 semiconductor platform. So we beam out directly, we laser on an orbital angular momentum mode. So a result that I will not tell you about most of those, but here Mohammed again will go through topology in detail and how these gauge fields are implemented. So usually topology, the Chern invariant, etc., are defined in periodic systems. So that is interesting. It works well. This is what we have used here. Those are periodic photonic crystals. So imagine that you actually now, in the context of laser, for instance, or you drive strongly the edge state. So at some point, it becomes nonlinear. So when you have nonlinearities, you actually break the orthogonality between modes. So, and then you basically lose topological protection. So because the edge state will now start to leak into the bulk. So that is problematic. It's not topological protected anymore. So what we found is, if you instead implement topology in a disordered array, so there have been ways to define topological invariant in this type of systems. If you do that, actually the edge state become more robust again. And a simple intuitive way to think about it is that in the bulk of a disordered system, you don't have a clear momentum defined. So basically the edge state cannot easily phase match to the bulk and stays in the edge. And there is kind of a resistance to coupling to the bulk that is introduced by disorder. So we have also extended the idea of topology to phase arrays that are commonly named now metasurfaces. So if you take, for instance, exceptional point, all the topology is based on basically the Berry phase around these singularities that are not used explicitly, but they are used to define topological invariant. So we have shown that you can actually use the Berry phase explicitly. So if you encircle the singularity with, let's say, particles moving in phase space of different size, so they will naturally implement a surface that is also a phase array. And what is interesting, because the Berry phase has some chirality into it, so if I send left or right circular polarization to the surface, I can do different things. So for instance, here we make a surface that can display different holograms depending on the chirality of light sent to the surface. So this is what I will tell you about, and I think this is the most important discovery of my group. So I am officially 10 years old. I've been faculty for exactly 10 years. So for the last 10 years, I think this is the most important thing that we have done. So I will discuss that a little bit today. So the idea is very simple. Usually we have a cavity. You can consider this room to be a cavity. And the cavity has boundaries. And the larger the cavity, the more mode you have, right? So imagine you want to make a laser. You basically put some kind of amplification mechanism in this box, and you start to amplify modes in the box. So semiconductors have a broad gain bandwidth, usually almost present in the cavity actually lays at some point when the box size increases. And this is a problem because if I want to make a powerful laser, the fact that I have many modes means that the laser is going to emit different colors. And that's not what you want. You want to put the entire power of the laser in a single mode so that you can reach larger distances and for various reasons. And unfortunately, this has been an open question for the last 65 years. It was believed to be not possible. I'm very proud that we solved this problem. I will explain details. And then recently, actually my postdoc, Walid, who started a faculty position recently, was the first to discover single photon emitters in silicon. People have worked on single photon emitters and are still working on them on various platforms, particularly in wide bandgap semiconductors. But here, silicon that is, of course, indirect gap. But you don't use directly the band edges of silicon. You use state that are localized in the gap, and we were able to emit single photons out. So this is a field that is growing, actually pioneered by my postdoc. So I don't need to introduce too much why lasers are important, just few things. So lasers are used in data centers. They are used for communication in space and on Earth. They are used for sensing. They are used for manufacturing. And they are used for quantum computing. They could be used. Those are theoretical proposals for light sails. And they have been used recently, not far from where I live, at Livermore, where ignition was achieved for the first time about 2 years ago. So, lasers are very, very important. They are ubiquitous. They are everywhere. Okay. So, just taking one of these aspects, for example, laser processing here is expected to be a market of about $50 billion by 2030. So this is just manufacturing here, and just imagine if you add everything else. But one of the issues, semiconductor lasers that are actually the most efficient laser we know have been unable to generate high power. They cannot generate high power. So in order to generate high power, we use solid-state lasers in general. And these lasers are not efficient. So they are about, let's say, 10%. Semiconductor laser can be up to 70% efficient. So imagine if you could make a semiconductor laser that was as high power as solid-state laser. So that would be a revolution. We are talking about the planet and how much conserving energy or producing energy in a green way is important. So semiconductor can significantly contribute to that endeavor. So confining light and waves in general is extremely important. It's everything starts there. The cavity controls the spatio-temporal dynamic of any laser. So what type of beam the laser will emit, how fast the laser can be modulated, that's mostly depend on the cavity. And there are various ways of doing that. So here are a type of cavity, ring resonator, whispering gallery modes. So that work just easy to understand, just based on geometric optics. It's just total internal reflection, Snell law. So light is confined here at the boundary and goes around. And these resonators can reach very, very, very high Q factors. And there are various ways. This is another type of resonator that is basically a band gap, a defect in a band gap. So you see the periodic system is a photonic crystal. And if you remove few periods, you basically localize the wave within a band gap, within a mirror. So all of these things work. They are based on dielectrics. Usually they have some finite size. So here are other type of confinement mechanism using metal optics or plasmonics, and some other systems here, a laser directly grown on silicon. So there are many, many ways to confine light on chip. So, but a question that that we have been asking ourselves in my group in the last few years is if the cavity could do more than just confining light. For instance, I show the example of the topological laser. The main idea for us was to make the laser not only be a laser, but also be the isolation mechanism, right? Because isolators are always present on chip to prevent light from coming back. That laser does not need any isolator. It is intrinsically isolated thanks to topology. So the bound state in the continuum that I did not really discuss in detail can be not only a lasing mechanism, but can also be a way to intrinsically do beam steering. There are ways to beam light with BICs. And today I would like to discuss an approach to make the laser the amplification mechanism. How to make high power laser. There are many ways to do that. For instance, a Nobel Prize was awarded to CPA, chirp pulse amplification. So you take a pulse, you stretch the pulse, amplify, and then after it is amplified, you compress it back. So that was extremely important. So the way high power is done today, usually using fibers, you send a signal, you pump a waveguide, basically, and as light propagates down the waveguide, it gets amplified. Very simple. So these work very well. Issues that these systems are facing is, as the power increases, when light propagates, at some point the power is so high that you trigger nonlinearities in the fiber, and then that leads to self-focusing, and it burns the fiber. This is working well. So something that has been a dream is to move from a 1D amplification to something of this kind, a single aperture system that can amplify emission. Why is that interesting? So here, of course, the power scale has the length, right? So you propagate and the light is amplified. In such a system, so power scale has the square of the linear dimension. Of course, this is more favorable and will lead to a more compact system compared to what can be done with a waveguide. So, but unfortunately, these approaches have not worked for a very long time, because as you increase the size of the aperture, what I was just telling you before, when you make the aperture larger and larger, you get more and more modes. So then how do you select? They're all lazy. It does not work. Okay, a lot of optimization has been done. I will discuss some of them. But essentially, there are fundamental issues that are preventing us from scaling these systems. And I want to go back. When a problem is hard, to go back to the origin. So the origin is this guy, Charles Tang, who was actually a faculty at UC Berkeley for over 55 years. Actually, he was still alive when I was a postdoc at Berkeley. Unfortunately, I did not get to meet him. So he passed away in 2014, I believe, at 99 in Oakland. So, and actually, he was coming to campus almost every day, almost until his death. Is that amazing? So what did it say? So this is the very first paper proposing the concept of lasers, and actually was awarded the Nobel Prize a few years after that in 1964. When you look at this paper that I advise you read, so look at here, a single mode may be selected. So actually, since day one, single mode operation for laser has never been guaranteed. Maybe. It's not sure. And then by defining a suitably small angular aperture, since day one, if you want to make a laser single mode, you have to make the laser small. And if you make the laser small, you will have small power. Okay? So this is from day one. So what I will discuss today is that we replace maybe by will be. And then what is said after that is not going to be true anymore. Okay? So that's the goal of the talk today. So again, so here, just taking a box. Just think of this box as being this room, and then the dashed white line are the boundaries of the room, okay? So the exact shape of the boundary doesn't really matter. Here it's circular, it doesn't really matter. So if you take such boxes, there is something universal. I mean, let me just take a single particle picture. Imagine I take a ball, a soccer ball. I like soccer. And I kick the ball here, the ball will bounce back and forth in the wall, right, on the wall, etc., and then come back. So imagine you want to catch the ball. So where are you going to sit? If you want to catch the ball, where will you sit? At the center. Okay? So if you sit at the center of the room, this is where the likelihood for you to catch the ball, bouncing back and forth on the wall, is the highest. And in a cavity, when you calculate the modes of the cavity, this is the fundamental mode of the cavity. You see the probability of the particle to be at the center is the highest. Okay? So, and actually this is the problem. So, I mean, there are many ways of understanding the problem. So finally we understood that this is the problem. So if you sit at the boundary, imagine again the ball is bouncing back and forth. So this is one boundary here, and I sit here, the likelihood for me to see the ball is extremely small. And you see it again from this picture, the field, the probability to get the ball close to the boundary is almost zero. This is the problem, okay? So this is why it has been hard to actually increase the power of lasers. Why? Because this is the fundamental mode, and the first higher order mode is here. And then, of course, there are many higher order modes. You take any potential well, it doesn't matter what the wave system is, electronic, acoustic, photonic. the fundamental mode is always of that kind. No, it's like this, and then the higher you go in frequency, the faster the wave oscillates. So because the fundamental mode is mostly confined at the boundary, and higher order mode, you see the first higher order mode, just to illustrate, is closer to the boundary. So if this was a laser cavity, so if you sit close to the boundary, you do not contribute to the fundamental mode. That is mostly at the center. But the cavity has gain everywhere. And the first higher order mode is extremely happy. Say, oh, since the fundamental mode is not using the gain at the boundary, I'll reuse it. Okay? So the way I usually explain it to my students is that, so if I think of you guys as being unit cell of this aperture, I am one unit cell as well, and I'm sitting here, I am a lazy resonator. Why? You see the guy who are close to the boundary here, they will never catch the ball, so they are lazy. Okay, so the lazy resonator will not contribute to the fundamental mode. And higher order mode would like that because since they oscillate faster, they take advantage of this lazy resonator sitting close to the boundary and use them to make the cavity become multimode or the laser become multimode. So you see, actually, this is in physics. There is nothing you can do, right? This is those are modes in potential wells. So what can we do? Potential wells are always like that. The waves are always oscillatory. So then there is nothing we can do. So when this type of problem happens, then you need new physics. So the way this is usually quantified is in lasers is we define a quantity called the threshold gain difference. Basically, the difference between the threshold of the fundamental mode and the threshold of the first higher order mode. So to explain for those who are not familiar with laser, in order to laser, you pump, you give energy to the system. You give some energy at some point, there is enough energy for the first mode to laser. And if you want the next mode to laser, you have to keep pumping, and at some point that mode starts to laser as well. But if you pump a lot, then everyone will laser. So, but what this plot is showing is when you make the size of the cavity larger, again the cavity is the room, if you make the size of the cavity larger, the threshold gain difference goes to 0 with the size. Meaning that at large size, actually all the modes become good. They will all laser. So high size, again, because I want to make a high power laser, if you increase the size, at some point all mode will laser. So regardless of the design and regardless of how smart you are, this will always happen. And the last 30 years, people have worked on photonic crystal laser, so I should give credit to Susumu Noda in Japan, who is the scientist who spent the most time on this problem. He has been the most serious, and he has amazing results. But fundamentally, this is actually a plot from his paper, the reference is here. Fundamentally, when the size of the cavity increases, this threshold gain difference goes to 0. So the last 30 years, what happened is that the design moved from something like this, a photonic crystal single lattice, to a double lattice photonic crystal to this one. So in 30 years, we moved from the black line to the red line. Did we make progress? Yes, we did. The two modes are now further apart, so we can pump further and get more power, but it's still going to 0 with the size, meaning that there is no way we can keep increasing the power. Actually, we have not increased power by a lot. So this is basic physics. It does not work. Current cavities are scale variant. So now I'm going to share how we look at this problem. So first, the first laser was invented, laser were invented in 1958. I just showed the work from Charlestown. And the first ruby laser was demonstrated by Menman in 1960. The first semiconductor laser in 62 by almost 3 groups at the same time. The first VEXEL, vertical cavity surface emitting laser by IGA in 79, and the first photonic crystal surface emitting laser by a group at Bell Lab and the group in which Noda was in 99. So what I claim is, in fact, that all these lasers, they all use the same principle. And then I call that principle the shallow towns to mirror strategy. They all use the same strategy. And how can you see that? So actually, go back to the lazy horizontal picture that I just gave. So this is an edge emitting laser. So light is emitted at the edge. You see the mode is emitted here. It's maximum at the center. When you go to the edge, the field goes to 0. So this is a VEXEL. You all have many of those in your pocket right now, if you don't know. So phones use those to do face recognition. So the field is maximum at the center and then goes to 0 when you go to the boundary. And then a photonic crystal surface emitting laser, the field is maximum at the center and goes to 0 when you go to the boundary. So all these lasers use exactly the same principle. They use the two-mirror strategy originally proposed by Charlestown. And because of that, actually, they all suffer from the limitation of the two-mirror strategy. So in order to really move away from that, so my student and I, myself, proposed this concept. So we call it the Berkeley surface emitting laser for Berkel. Sorry, that's the name we chose. And then, as you can see from the image, there are no lazy resonator in the box. So you at the center of the cavity and myself here at the edge of the cavity, we are contributing exactly the same way. So this was thought to be not possible, but it is in fact possible. We'll discuss it in the minute to come. And this actually solves the scaling problem of semiconductor laser because you make the box larger and larger, the mode will extend everywhere in the box. So there is no dead spot in the box. There is no spatial hole burning in the cavity. So the cavity is scale invariant. So in principle, there is no limit to how much power a semiconductor laser can emit. And for me, this is an amazing news. So what is the idea? So the idea is not easy to understand, but actually it's not very complicated, but I try to simplify it. So I'm an electrical engineer. So let's take a transmission line here that is basically a coaxial cable. Everything is transmission line, including air. Anything that propagates a wave is a transmission line. So here I take, just to convey the idea, imagine you take a coaxial cable. It does propagate a wave, right? At home, that's what you use for various things, at least before. Things have changed today. So the wave propagates. And if I want to transform this transmission line into a good cavity, I have to close the channel via which the wave can escape. For instance, the wave propagates in the transmission line, and at the boundary here, it may escape. So how do we construct cavity? The two-mirror strategy. We close the boundaries and put mirrors and force the wave to bounce back and forth between the mirrors. The news, that is a bad idea. Okay? So that's what we have done, but that's not a good idea. So why? Because when you put mirrors at the end of the cavity, you actually create a standing wave that is maximum at the center again. So those mirrors prevent the cavity from scaling. So instead of putting mirrors, so we propose a kind of counterintuitive idea. So I would like to terminate my transmission line with a match load. A match load. So imagine a transmission line that is 50 ohm. So I terminate it with 50 ohm. So initially you will also tell me this is a bad idea because a match load consumes power. So I want to make a good cavity, but I'm putting something that is consuming power. So that may not be a good idea either. So I will explain why this is a great idea. Okay? So if you actually put a match load, so you see this transmission line is one-dimensional, and the match load that I put here just for illustration is 0D. So power increases in the transmission line at a rate that is faster than the rate at which it is lost at the edge. So even if I am losing power at the edge, this is actually a great cavity. When I will increase the size, the amount of power in the cavity will go up. And then if you ask any undergrad to plot the standing wave in this cavity, I teach electromagnetism, so this is what the student will plot. So when you put a match load, there is no standing wave. So again, so if you are sitting at the center of the cavity here, and I'm sitting at the edge, you see the standing wave, the wave we are contributing with the same probability to the mode. So that is the idea. So these cavities solve the problem. So this is easy to plot. So how do we do it? So and this is actually a computation of such a cavity. You use a photonic crystal. You see this is the fundamental mode of the box. So this fundamental mode, surprisingly, we know Maxwell equation and Schrödinger equation for more than a century. So it's very surprising to me that in more than 150 years, no one predicted a mode of this kind in any potential well. This is really surprising. So it has not been predicted by any theorist. It has not been measured by any experimentalist. So we are in the day of AI. So it has not been predicted by AI either. Okay. Because usually AI is good at predicting what we already said before. So that is it's a really a big surprise to me. So this is the result. So again, this mode performs total synchronization in the aperture. So all elements in the aperture are in phase and have exactly the same amplitude. So now let me be a little bit more technical. So usually, what happened is that electronic or photonic system have a quadratic dispersion close to the band edge. And actually, that quadratic dispersion close to the band edge governs everything. It governs the Q factor of the modes. It governs mode spacing in the cavity. So I will go to detail later on, but when you have a quadratic dispersion at the band edge, we'll explain that mode spacing scale as the square of the wave vector, and the quality factor of mode, when the size of the cavity goes to 0, become all the same. They're all large. And what we propose is to move to a system that has linear dispersion at the band edge, which is reminiscent of graphene for electronic systems. And in that case, mode spacing will scale as the wave vector, okay? But that's not enough. People have thought about this before. The most important thing is that what I call the imaginary free spectral range will not go to 0 with the size. So we'll go to the details. So here is a system of size D. It's a photonic system. The size is D. And then the system has a dispersion that is quadratic at the band edge, meaning that the frequency depends on the wave vector as quadratically. So, and delta omega 2, so the first mode in this system is at pi over D, and the second mode is at 2 pi over D, etc., etc. So the mode spacing, delta omega 2, the frequency separation between the fundamental mode and the first higher order mode, is delta omega 2 again, 2 like quadratic, and the scale as 1 over D square, where D is the size of the aperture. So then the problem is there, right? So the mode spacing scale as 1 over D square. So D is the size of the aperture. If I want power again, you make D larger and larger. But when you make D large, mode spacing goes to 0. Then all the modes are so close that they will always doesn't work. So instead, if you move to a system with linear dispersion, you see immediately that when the dispersion is linear, delta omega, 1 for linear, is slightly amplified. Then, and then you can calculate, you find that delta omega now scale as 1 over D. 1 over D is better than 1 over D square when D is large. They say, oh, we solved the problem, but not really. Because 1 over D also goes to 0 with the size. And actually, if 1 over D was better, for specialists, exceptional point, for instance, have a sublinear dispersion, then they will be even better, but we know that they don't work either. So that's not enough. So in fact, that's not enough. It is necessary, but we show that it's necessary, but it's not sufficient. So the only slide with equations, okay? So imagine you want to form something with linear dispersion. You take the first order overlap between two modes that I call Ui and Uj, and the dispersion, the Hamiltonian can be written that way, where delta is the detuning of the mode, is led to the little gap here, and beta is the group velocity. So in order you plot the eigen values of this as a function of parameter k, you see that you do get linear dispersion with k. Now, so if you look at the eigenvectors of this system, this is what is interesting. So the modes are Ui and Uj, but you see that the eigenvectors are yellow everywhere. Yellow means that they are mixed. So there are everywhere a linear combination of Ui and Uj. Okay? Except at the gamma point. If you look carefully, close to k equals to 0, actually modes are not mixed, they are pure. They are either Ui or Uj. So actually we solved the problem. See, just take a 2 by 2 matrix. But you have to look at it very carefully. So imagine that you could implement this linear dispersion so that the top band, for instance, is more lossy, has more loss, and the bottom band has less loss. Because it is the linear combination of the two bands all the time, then the dynamic is mostly going to be governed by the loss by the mode that is more lossy. So actually, a simple image. Imagine I have a lot of loss, and Bill has low loss. Okay? And separately, he has low loss, I have a lot of loss. Now, if the modes is the linear combination of the two of us, I am more lossy, I will dominate the dynamic of the modes. And this is what we do here, because since the dynamic, we don't do it yet, if I could implement one of the bands so that it is more lossy, then actually modes are going to be mostly lossy everywhere, but except at the gamma point here, they will be pure. So we have damped a lot of losses in higher order mode that, of course, have to be at wave vector larger than 0. So that's easy, but there is a fundamental problem also. The belief right now, there is a fundamental difference between electronics and photonics. If I take a graphene sheet, okay, you take a graphene sheet, and at the boundary of the graphene sheet, when you do an experiment, the electrons do not jump out of graphene, right? When you take a graphene of finite size, electrons stay in graphene, regardless of the size of the system. In photonics, if you implement linear dispersion for photons, at the boundary of your finite-sized crystal, photons do not stay in the photonic crystal. They escape. So because of that, the belief was that as soon as you have a finite-sized photonic crystal, actually you don't get Dirac point anymore. You get exceptional points. And then the linear dispersion is gone. You see, now you get a sublinear dispersion, which is a square root. So I will not go to detail, but what we found is that if you implement these Dirac dispersion with modes that do not radiate at the gamma point, it is possible to maintain the linearity of the band in the presence of losses. But I will not go to those details. But that was the key. So this is a photonic crystal, a scanning electron microscope image of a photonic crystal that has linear dispersion. Theoretically, this is the dispersion of the system, linear dispersion at the band edge. And what I will explain is that exactly at the gamma point here, the fundamental mode is sitting there. Not near the gamma point, at the gamma point. This is very surprising. This is a not unconventional quantization. The fundamental mode is here, not at pi over L, at 0. And that not only is that possible, but that mode is actually going to be the fundamental mode of the cavity. It will laze, and because the mode is everywhere, there is actually no space, no gain left for higher order mode to laze. Another way, I mean, let's move on in the interest of time. So that was the infinite system. What I have shown was the dispersion of the infinite photonic crystal. But that does not exist in practice. In practice, when I do an experiment, actually, if I want a cavity, I need boundaries. So you have to be careful in the way you construct the cavity. So here, the two bands that were contributing to the formation of the Dirac cone, one band has a C6 symmetry and the other one has a C2 symmetry. So if you truncate the infinite photonic crystal into something that is, let's say, an hexagon, so this hexagon will preserve the symmetry of one of the bands, but it is mismatching the symmetry of the other band. So meaning that it will implement what I have shown you on the 2x2 Hamiltonian is that by mismatching the symmetry of one of the bands, you naturally make that band more lossy. So we call this an open Dirac cavity. So, and actually the cavity is just the hexagon. So this is a device that was fabricated, it is suspended in air and fabricated in the indium phosphide platform. Those are indium, gallium, arsenide phosphide, multiple quantum weld that are grown epitaxially on indium phosphide. So if you take the linear dispersion system, so then when the cavity is of finite size, you don't have a band anymore, you have modes. And the fundamental mode is sitting exactly here at wave vector 0. And the higher order mode, of course, are sitting on the dispersion as well. And here is the result. The fundamental mode, as I predicted in the previous slide, now you see here, is everywhere in the box. There are no lazy resonators, regardless of the size. For a small box, larger box, the mode is everywhere. So there is no space in this cavity for higher order mode to come into the picture. So if you make a laser out of it, the laser will be single mode regardless of the size of the cavity. That's the idea. So just to summarize what I have said so far, so this is what we call an open Dirac cavity. It is obtained from system with this type of linear dispersion, but that do not lead to exceptional point when the system is of finite size in the presence of radiative losses. And the laser that correspond to this platform, we call it the Berkeley surface emitting laser. So we basically discover a new solution in a potential well that has not been predicted before, a solution that has a flat envelope. So if you look at the dispersion of these cavities, those are things that I have said before. So the mode spacing as a function of the size of the cavity. So when the dispersion is quadratic, what has been conventionally done in photonic crystal or in bound state in conductium laser, etc. So mode spacing scale as 1 over d square. I've demonstrated that before, or k square. And when the dispersion is linear, mode spacing scale as 1 over d. We have shown that before, or k. But you see in the two cases, delta omega, which is the separation between the mode, again, with linear dispersion is slightly better, but it still goes to 0 with the size. So that's not good enough. So the key with these open Dirac cavities is to look at the imaginary part of the free spectral range. Something that we don't do. If you take any optics books, no one will do that. So let me tell you again, cavities, they have a Q factor, meaning that the eigenmode is complex, meaning that it has a real part and an imaginary part. Right? So now when you calculate the free spectral range in books, why do we forget about the imaginary part? We only calculate the free spectral range based on the real frequency. So that's not correct. I mean, it's correct because for cavities, we know it doesn't really matter. But in this particular cavity, the imaginary part is the secret, because you see, since we are dumping losses into higher order mode, in all cavities that we know today, the imaginary part of the free spectral range actually goes to 0 with the size. But in the open Dirac cavity that we just proposed, this imaginary part of the free spectral range is scale invariant. This quantity here does not decay with the size. So actually, I extrapolated here. This is what happened with the size. When the size goes to infinity, the imaginary part of the free spectral range converges to a constant value. And that value is governed by the loss rate of the two bands that contribute to the formation of the Dirac cone. This is really amazing to me. So I say, oh, okay, that was theory. So we say, okay, people will only be convinced if you can really prove this experimentally. So we did. So we fabricated various cavities. So our Dirac here is, so here this is the photonic crystal, the one that I have shown you. The parameter we use to tune the dispersion of the band is the radius of holes. So for some hole radius around our Dirac, the dispersion is linear. And then when you move away from that, smaller or larger, the dispersion becomes quadratic. So when the cavity is small, there is no problem, right? When the cavity is small, it's not difficult to make a small cavity single mode. All cavities are single mode regardless of the band, the curvature of the band. We made lasers, you see they are single mode. And then we increase the size of the cavity. And you see, it's still small enough, they are all single mode. And then we increase the size of the cavity. Wow, look at what is happening. So it is multi-mode when the dispersion is quadratic. And around the open Dirac singularity, it is still single mode. So at this point, we are very excited. We submitted the paper, and some of the reviewers say, maybe you have been lucky. We want to see this behavior to continue. They say, okay, we are not fully convinced. No, show that this still happens when you make larger cavities. Okay, we have to go to the clean room again, make more cavities. Okay, so let's so. Again, so this diameter is about 40 micron. So just for your reference, VEXELs that we use every day today, the aperture size of a VEXEL is about a micron. So if it is larger than 1 micron, it's already multimode. Okay, so this is already 40 times the diameter of a VEXEL. So, and then we increase again. After the reviewer request, you see it's multimode when I am detuned from the Dirac singularity. When I am here, it's single mode. And then we increase again. It is multimode when you are away from the Dirac singularity. Around the Dirac singularity is still single mode. So what we claim is that Berkeley are in principle single mode, regardless of the size of the cavity. So, and this is the first ever such cavity. A semiconductor laser that can be single mode, regardless of the size. So this is summarized on this plot here. Again, around the Dirac singularity, we will have single mode behavior, regardless of how large you make the cavity. Of course, there are issues, manufacturing challenges that we are working on if you want to make the cavity even larger, but I think this is an amazing news by itself. So, and then we computed the far field. This is what theory predicted, and then we measured the far field. You see, this is exactly like theory. So a cavity that is small, larger. I just took few of them. So again, the far field is nothing but the Fourier transform of the near field, right? The envelope is flat. So when you make the cavity larger and larger, the divergence goes down. The beam is less and less divergent. So this is reciprocal space, and this is the image of the cavity in real space. And conventional cavities are like this. As I said, active people at the center, lazy resonator on the boundary. And when you do that, you see, of course, it's basically like a defect. Now we have a flat envelope in the entire box. So that means that we have less divergence. Actually, the far field is diffraction limited. So it diverges exactly as 1 over d, where d is the size of the aperture. Okay, so yeah, that's what I wanted to share today. So I think we discovered a new type of semiconductor laser that is what I call scale invariant. So it will be single mode regardless of how large you make the cavity. And in principle, so that means we could in the future make extremely high power lasers for many things, good or bad. But I'm thinking about the good things. So, yeah, so that's the news today. So let me stop here so that we can have some time to ask questions. So, and actually maybe an important slide here. So I have to thank the great students I am lucky to work with and who are contributing to most of the work I'm presenting here. Of course, it's a partial picture because the group is dynamic, the number of people, etc. Everything is changing every day. So, yeah, so let me stop here and take questions. Thank you.
So I'm going to take liberty and ask the first question.
Great.
Because one of the things that struck me about your description of the way that Dirac point is structured, that fundamental mode looks like a flat band.
So there are, usually when people talk about flat band, they are talking about flat band in reciprocal space.
Yes.
This is different. This is flat in real space. It is the mode that is flat. So very, very different. Right? So the flat band that we use for twisted electronics or for increasing correlation between electrons, etc. So this is different. This is a flat mode in real space. Okay, just go back to the ball picture that I was talking about. Okay. Yes.
So you kind of alluded a little bit to the complications of the aperture, increasing it in size. What are those types of difficulties that you've been facing to scale the aperture to essentially make it even better and the scaling of 1/d?
Yeah, so that is a great question. Indeed, in order to explain in this paper exactly what the symmetries of the mode are, things to be very clean, we decided to work with a suspended membrane so that we have symmetry for the cavity. Here it is air on top, you have the semiconductor multiple quantum well, and the substrate is H, so it is also air at the bottom. So of course, if you want to make this cavity larger and larger, since it is suspended, at some point it will collapse. Right? So that's not ideal. So if you want something to scale, if you want to scale, you have to put it on a substrate, etc. Those are things that we are working on now that are done. So there's really no fundamental issue, right? So if you do E-beam lithography, when the size become larger and larger, you have proximity effects, it becomes harder to get exactly uniform systems. But nothing that is really out of reach. This is what I really like about the platform because it is a photonic crystal, the dimensions are comparable to the wavelength. So we will really be able to make this in the coming years with some relative ease, I would say. But there are other issues. So we need to make this laser electrically injected. If you want something to be useful, this was still optically pumped. So those are questions that we need to think about as well. That are not necessarily very simple, but we are working on them as well.
Small follow-up to that same premise. Would you putting it on type of substrate not affect the modes?
Yeah, exactly.
Okay.
So because you need some kind of mode confinement, so if you need some index contrast, so meaning that you cannot just put it in random substrate.
Okay, thank you.
Yeah, those are things that can be done.
Great talk. Thank you.
Yeah, thank you.
Thank you. Thank you for breaking down the problem. I really appreciate how you did that. So I have a question. When I saw that mode, I immediately thought of an E and Z material, epsilon near zero,
Okay, very
right?
good.
So
Very good
the question is, did you effectively make like an effective refractive index?
So that is a great question. You guys are so great. I love it. So, actually, I have evolved in my career quite a bit. I did my PhD in France at Paris-Saclay, and I used to work on metamaterials, so I know E and Z pretty well. So E and Z for epsilon near zero. So this is a concept that has been popularized by people working in the metamaterial community. But so this is not an E and Z. This is not epsilon near zero material. This is an exactly zero index material. So there is a fundamental difference because actually the idea is simple. Actually, if you look at the Dirac dispersion here, so let me, so if you look at the Dirac dispersion here, so it's a Dirac dispersion. If you take a constant omega plane, constant omega, it will cut the cone and the intersection with the cone will be a circle. So the radius of the circle is basically the effective index of the aperture. Yeah. And then if you come at the Dirac point, the effective index is exactly zero, okay? But everything, why people say epsilon near zero? Because they cannot get zero. Because when you actually truncate a Dirac, people have tried, but the conclusion was that it's actually never zero. The mode is always localized somewhere. Yes. So then we say near zero. So near zero is not good enough. Because any resonator is near zero. If I take a plasmonic resonance, it is epsilon near zero. If you take a split ring resonator with a magnetic resonance, it is mu near zero. So near zero is basically another name for a resonance.
Okay. All right. So I appreciate that. Now, follow-up question with that is when you spread out that mode, especially with these really large service areas, I imagine, and correct me if I'm wrong, that the enhancement's actually going to go down. Like, so because you're lowering confinement of your mode. So even though you have more power, you are essentially, you need to also pump it more to get to more power because you have enhancement. I wanted to know if you could speak a little bit about that. Maybe enhancement is overrated. Maybe it's not as important as we think, but.
Okay, great question as well. So this is an extended cavity. So I don't know if you are thinking about enhancement in the per cell sense. So this is not a per cell enhanced system because per cell is Q over V. So Q is high here, but the mode volume is large. So so pumping higher. Yes, indeed. So there are two ways to get more power out, right? So one is I pump the same way. The pump power density doesn't change, but I increase the size of the aperture. That can be done, right? So I have a constant pump power density, and I just increase the size. So I get more power out. The other way is I keep the same size, and I pump harder. Okay, so in all the systems we know so far, that doesn't work because if you pump harder, then you start exciting higher order modes. So in this system, so actually this is something I did not say, so thank you for the opportunity. So here, what we found is that we can pump this cavity up to the damage threshold, and it doesn't become multimode.
No gain.
No, because there is no gain left for higher order mode. So when you start pumping, the fundamental mode eats the gain. And then you pump harder, it is more gain until gain is completely depleted. And then there is no gain left. So higher order mode that exists in the system, they don't see any gain, they cannot laze. So that is also something great for this cavity. It will remain single mode regardless of how strongly you pump the cavity, which is not the case for existing lasers.
Until it bursts into flames.
Exactly. Exactly.
Great.
Just one more question.
Oh, great talk, Dr. Kante. Nice
Hi,
to see you.
Moses. Great to see you as well.
Nice to see. I worked at this when I was at Bell Lab, so it's nice to see 20-something years after that
Great.
to see this.
Great.
Could you talk through what would be required to make this, to electrically pump these lasers?
Okay,
And what kind of efficiencies do you expect to get?
So fundamentally, this is a diode, right? So the type of efficiency, I don't expect any breakthrough for efficiency compared to existing diodes. So they can go to 50, 60% efficiency. That's what we can get with these lasers. Now, there are indeed complications when it comes to electrically injecting them. So I don't know if I can reveal everything, but we are working hard on that. So a simple complication is, okay, let me say it. So one simple complication is, since the mode is everywhere, so where do you put the electrodes? Okay, so I mean, we have a solution for that, but I will not share it with you today. But you can build what is done, I mean, similar to what is done with our system, you build a PN junction. You have to build a PN junction to inject carriers and get them to radiatively recombine in this mode and get it to laze. So this has not been achieved yet, but we are working on it. Okay, great question.
So let's thank Professor Kante again. So our next speaker this morning is Professor Mohammed Hafezi, Mina Martin Professor of Electrical Engineering and Computer Engineering at the University of Maryland. Also, I did a joint appointment in the physics department at the University of Maryland. Professor Hafezi is actually a former Harvard guy. I'm not sure. So were you in Misha's orbit?
Misha and Eugene Demlet.
Yeah. And so unfortunately, I keep inviting Harvard guy, so I apologize for that. But more importantly, he's one of the primary drivers of the Maryland Joint Quantum Institute, which I guess I would probably let you better describe kind of what's going on in the community at all at University of Maryland. So I'll get out of the way and let Professor Hafezi go ahead.
Thanks for the introduction. Indeed, I am from University of Maryland, the Joint Quantum Institute. It's an institute between University of Maryland and NIST, National Institute of Standards and Technology. So half of the groups are University of Maryland based, half of them are National Institute based, the national lab that belongs to Department of Commerce. So what I'm going to talk about is topological photonics. Is some of it, it's the work that we have done in our group and my collaboration, but I would like to give a little bit of a broad introduction to the topic. And I heard good questions, so I think I hope you would like it. So this is a long project for the past 10, 13 years. Basically, once I left here. So I will mix it with a little bit of a personal history in case it's interesting. I should finish at 5 p.m., right? Is that good? And I can take questions. Please interrupt me. Yeah, please interrupt me if there is a question. I prefer to not finish the talk. So like 10?
Well, we have a break at after your talk, so if you overrun, you'll be fine.
No, but okay. Well, you shot me, basically. Otherwise, I will go forever. So again, like Boubacar, I would like to give a very, very brief introduction to the work that we are doing in our group. Part of it is topological photonics, which is the topic of this talk. It's a mixture of theory and experiment. We also work on theory of quantum simulators, what kind of interesting models we can implement in quantum simulators, and in particular, how we can measure them. Because I'm trained as a theorist and a physicist, and usually you have ways in condensed matter physics or optics to measure things. But with these quantum simulators, we have to think really differently. We are beyond linear and nonlinear response theory. We have access to the wave function, so we can do really crazy things that are not possible with the real material. And then if I have time, I will also highlight some of the new directions in the lab, which is basically, again, a theory and experimental mixture. And that's the idea of applying quantum optics to correlated material. So quantum optics is well established, particularly thanks to quantum information sciences, because we want to manipulate individual electrons, individual spins with light, with individual photons, etc. But can we bring this kind of technology and science and know-how to material? Can we manipulate, probe many body states of electrons using quantum optics? Can light, for example, drive the system into a correlated state? Can it induce interesting magnetism, ferroelectricity, superconductivity using light? So this is a kind of a new direction that we have started at Maryland, and it's going about many other groups around the world that are working on this topic. So topological photonics. I start with something simplest as possible. The building block of a photonic system is a resonator. Okay, you can think of a resonator like what we heard in the previous talk in photonic crystals. You can think of also ring resonators. These are silicon on insulator systems. So these are waveguides that are bent on themselves, then form a resonator. You can couple them to each other. You can have these micro resonators. You can have gallium arsenide photonic crystal formed in terms of exciton polariton, or you can think of the microwave domain. I think Will Oliver talked, right? That would be like, again, a resonator, but that's in a different frequency. They're highly nonlinear. We can couple them, and we can ask. That's just the building block. But what I'm going to talk about is kind of agnostic to the frequency, and one can implement them in any frequency scale you like. We want to study topology. Okay, so very like on a very high level and a simple level. When objects have the same topological property, we say that they can be connected with the continuous deformation with no cutting and gluing. Okay, so the usual example is the coffee mug and a donut, etc. And I'm bored with that, so there is another one. So I hope this one is more illustrative as well. So regardless of the shape of an island, we call it an island. If it's heart shape, rectangular shape, square shape, doesn't matter. As long as you have a piece of land in water, we call it an island. If that land is connected to the mainland, we call it the peninsula, almost an island. Okay, so they're topologically distinct. We have two different words to describe two topologically distinct situations. Okay, so what? What is different, can we characterize them differently? Imagine that it's a nice summer, you're swimming around this island, you start at what point, and then you go around the island either clockwise or counterclockwise. Regardless of the path you take, and regardless of the shape of this island, you always do an integer number of laps around the island. It can be positive or negative if you sign the circulation. But if you want to do it with a peninsula, that is 0, okay? So there are integer numbers that you can assign to these things. And if the game of the topological physics is that if you can assign a physical observable to these winding numbers, then you're gold. Because then your physical observable will only depend on the winding number, or these integer numbers that cannot be fraction or irrational or anything else. Okay, so that's kind of at the very, very high level, the goal of topological physics, to relate physical observables to some things that is an integer. Okay, but that was not how we discovered topological physics and topology in physics. It was the other way around. There was an experiment, and then people realized it's related to topology, and that's the famous example of quantum Hall effect. So you have a two-dimensional electron gas, you have a magnetic field perpendicular to it, you run a current in this direction, you measure the voltage in the opposite direction, and then you have this Hall resistivity. And when you look at this Hall resistivity as a function of magnetic field, what was observed was the following. Instead of the classical prediction, it would be just a simple line, but instead of a simple line, what was observed is the appearance of these plateaus, appearance of these steps. And what was interesting was that regardless of the temperature, of course the temperature should be low, but it doesn't have to be specific value. And regardless of the shape of the sample, regardless of the amount of impurity, again, as long as the impurity is not too high or too low, you see the appearance of these plateaus. And what is interesting is that they're related to some fundamental constant, h and e squared, and some integer number. And that's actually the only example in topological physics where it has some usefulness. So far, we have not been able to make a use of topology, except the standard for resistance. I think I'm talking also for the NIST part of JQI. But it has so many interesting fundamental physics. It's an amazing topic. Quantum Hall physics has been going on. I should not talk when Bob is here. That it is amazing that how many interesting physics has come out of quantum Hall effect. Just a simple two-dimensional electron gas with a magnetic field. It's just mind-blowing, and it's going on. So one way of very simply understanding why this robustness comes about is that when you have a magnetic field, the electrons are doing cyclotron motion, so they don't contribute to the conduction. But if the electrons happen to be at the edge of the system in this semi-classical picture, they would follow this skipping orbits. And as long as I have some edge, the skipping orbits would find its way and go around the edge. So if the edge is dented, imagine that you have some dent over here, still you have an edge, so the skipping orbit will go around it and then continues its way. And as long as you have the nice edge and it's not super destroyed, then you have your robust conductance. So the question that we asked a long time ago was that is it possible to have this for photons? Photons don't have charge, and as Boubacar said, the magnetic field acts on photons, but it's usually weak. How can we think about these problems? And is anything useful that could come out of this? So for that, let's just zoom out. What is a generic photonic system that you have, like a fiber or a waveguide? You have your light coming and propagating peacefully, and then all of a sudden there is some impurity, and it can easily backscatter in the reverse direction. So can I have a topological photonic system where if I have some impurity around it, it would, instead of getting backscattered, it would go around the impurity and continues its way. So that would be kind of like a generic approach for a photonic system. Can we make robust models? So if you're just looking at the single particle physics, like just photons, no interaction, etc., we're actually looking at the robust solutions of the Maxwell's equation. So Maxwell actually could have thought about topological photonics many years ago. It's just it took us from Maxwell to quantum Hall effect, to understand that it's related to topology, to write a Hamiltonian model, and then realize, there are some solutions that are topologically robust. What do I mean? I mean that if I have some dielectric fluctuations, if my dielectric constant changes in a space to some extent, my state, my wave functions, my modes are robust against those perturbations. Okay, this is at the single particle level. Things get more complicated and more interesting as we go along, but on the single particle level, that is the case. So how can we tell photons to feel an effective magnetic field? As I said, the magnetic field would, electrons would have cyclotron motion. You have Aron-Bohm effect. You have a magnetic flux. The electron goes around it, acquires a phase. So if we tell our photon to acquire the same phase, we should expect the same physics. So imagine I have an array of ring resonators. So these are some waveguides bent on itself to form a resonator. Some of them have some length. The other ones have the other length. So I tile them, I color them differently, some gray and white. And the game is that I would like the photon to go around this square and acquire a non-zero phase. If I manage to do that, then it's as if there is a non-zero magnetic field acting on this photon. So how do you do it? It's very simple. Imagine that I have one resonator like this, one resonator like that. M is an integer number. Lambda is the wavelength, resonant wavelength of light. And I connect it with a resonator that is exactly detuned by lambda over 2. So the total length of this has a lambda over 2 excess. So for those photons, this middle resonator is anti-resonant. So what happens is that if the photon is circulating like this, it can scatter into this waveguide, it comes here, but it won't go back immediately because it's anti-resonant. Instead, it will circulate a few times in the other resonator, and then when it wants to come back, it will take the lower path. So when I go from left to right, I take the upper path, and when I go from right to left, I take the lower path. And as long as I put this waveguide, this resonator, asymmetrically between these two, when I propagate from left to right, I acquire a phase that is different than when I go from right to left. And that asymmetry can help me to write a phase that is acquired by the photon. So in the second quantized formalism, again, we don't need it, but it's nice to see it. When the photon tunnels from left to right, it will acquire a phase alpha. When it hops from right to left, it would acquire plus alpha. These are the creation and annihilation of photons in resonator X and X plus 1. And kappa is the decay rate of the photon from the resonator into the middle resonator. So by engineering these waveguides, how close or how far away from each other, I can increase or decrease the value of this. So if you accept that for one link, I can imprint this phase, then I can tile the whole system and have a Hamiltonian like this, such that when I hop here, 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 I would get a non-zero phase. Sounds good? And I would do the same for this one, this one, this one. And this is as if I have a uniform magnetic field impinging on this two-dimensional system. Okay? So this is a Hamiltonian for our photons, but this is exactly can be a Hamiltonian for a single electron hopping on a square lattice with a non-zero magnetic field. And that is known from the 60s. The spectrum is called Hofstadter butterfly, after Douglas Hofstadter, when he was still doing physics. And alpha is the strength of the magnetic field, and this is the energy of these states. So if you put the system on a periodic boundary condition on a torus, you will see that you have these bands, you have these bands, and you have these bands. And if the magnetic field is fixed, you just see these states. Now, can we actually make this? Yes, we're using silicon and insulator technology. So this is a SEM image. This is a scanning electron microscope image. So it is actually an actual system. The length scale over here is 30 micron. The operating frequency is 1.5 micron. So you don't see this asymmetric positioning of the middle link resonators, but they are actually asymmetrically positioned. And we have made them in such a way when they go around this single plaquette, they will acquire a non-zero phase. So what is different is that we are working on that length scale that is much, much bigger than the electronic system. Also, our resonators are leaky, which is a good thing and a bad thing. The good thing is that they can leak out, And if we put a microscope, we can actually see where the photons are. So we can measure the wave function, the amplitude of the wave function on each side. So depending on what frequency of light I send in, I can excite one of those modes that we had in the previous slide. And then you can actually image it by using an IR camera. What is now interesting and robust about these systems is that not when they are on a torus. Imagine that it's just an open boundary condition. So I solve that Hamiltonian, I find the eigenstates, and I looked at them, and I see that when I put it on a square, not only I have these magnetic bands, but I have some states that appear over here and appear over here. If you look at the current, or in the photonic language, the Poynting vector of this electromagnetic wave, you see that these ones are circulating this way, and those ones are circulating in the opposite way. And I told you that it's like an effective magnetic field, right? So if the magnetic field is, let's say, positive, if these are circulating in one direction, it would have a different energy than if they're circulating in the opposite direction, right? So that means that if I put now an impurity over here, and the photon comes in and I would like to backscatter, the backscattering state has a different energy, and it would be very costly. So I have to do an inelastic scattering of photons, which is very expensive. So then instead, I should continue my way. I should go around the impurity and then continue my way. And that was what we observed experimentally. This is many years ago in 2013, that if you remove one of these resonators, instead of light getting backscattered, the light will actually go around it and then continues its way. So this is a simulation, and this is the experiment. Again, this is our old data. We have much, much better understanding of the system and better images now. So this is the platform that we have been using, and it has been very useful because not only we image these edge states, but we also could measure the corresponding topological invariants, those integer ones that I mentioned very at the high level in the island slide. One can actually look at the spectral flow and then measure the winding number. One can have something like a Haldane model where on average there is no magnetic field in the system. Instead, the magnetic field is staggered. One can also use it for exploring topological lasers and also reconfigurable systems. But this is one platform. There are also many other platforms, including helical waveguides, open cavities, what Boubacar is working on, to explore topological physics with photonics, different frequency domains, etc. As I mentioned, it's really agnostic to the value of the frequency. There are many explorations on this, like different platforms and different frequencies. So what I would like to focus going forward is that what can we expect beyond Maxwell's equation, beyond single particle physics when we add nonlinearity, and some physics that is not really, that does not have any electronic equivalent, because we were inspired by integer quantum Hall effect and even fractional quantum Hall effect. But can we have something that doesn't have topological electronic equivalent? In order to put this into perspective, I would like to show how one can think of quantum optics, different regimes of quantum optics. On the x-axis, you have the photon number, how many photons you have in the system. And on the y-axis is how strong photons interact with each other. Photons don't interact with each other. They interact with matter, and matter mediates interact between them. But that's very weak because the fine structure constant is weak. So usually we are operating in this regime. So photons interact very weakly with these two-level systems. And then we have to put a lot of photons in the systems to see some appreciable effects, like solitons, lasers, etc. But what you can do is that you can cheat. You can put your two-level system inside the cavity, and the cavity, we were not smart enough to make flat modes, which is the duck-shaped mode. But the goal is that now this photon is trapped. It has to do many round trips before it moves out. So you kind of amplify the fine structure constant by keeping the photon in the system. So it's just not one chance to interact with the matter, but many times. And that's basically the cavity QED regime. And if you have many photons, then you have many-body quantum optics. You can use the same axes for topological photonics, basically. That was kind of the motivation to show you this slide. So what I just showed you about imaging the edge states was just at this corner. You have weakly photons interact with each other and not many photons. But then you can go in this direction. You can add more photons. You can think about like topological lasers, solitons, and what I will talk about, frequency combs. Or you can go in this axis. You can couple two-level atoms or two-level systems like superconducting qubits to these topological edge states, and then look at their behavior and maybe create fractional states of them. So far, the world record is that has a Lofton state of 2 photons have been created. It's not a big system. So the goal of the community is kind of to explore what's over here. So this is kind of, it's moving in that direction. Okay, so I'm not going to talk about all of them by the speed that I'm going about these 3 topics basically. Any questions so far? No? Great. Okay. So the first one is photon pair generation. It's useful. We want to generate pairs of photons. I don't want to motivate quantum information sciences, but just I'm sure you're bought on the idea. So one of the ways to make photon pairs is to have a nonlinear system, and you pump it optically, and then you generate 2 photons. So you absorb 2 photons, you emit 2 photons. And this process is efficient if we satisfy momentum and energy conservation, obviously. So energy conservation means that omega p plus omega p is equal to omega s and omega I, and then the momentum is also conserved. Conservation of momentum in optics is basically called phase matching. Like the incoming momentum should be equal to outgoing momentum. If you like Hamiltonians, this is the Hamiltonian that you have. If you have a ring resonator, you pump it. These are the different resonators. These are different modes of the resonator. You can think of them as whispering gallery mode that have different windings. Yeah. So if you have a resonator, it can wind once, or it can wind more times, etc. So these are those modes. And one way to enhance it is to have a longer system. So instead of one ring, you can put many rings and couple them to each other. You pump it on one side, and then you generate these photon pairs. But these are nanofabricated systems. They're hard to fabricate. It's just, you show one slide, but there's a lot of work behind it. So when you fabricate them, and then you look at the joint spectral density of the emitted photons, like how strong photons are coming at omega I and omega S, then you repeat it for 2 devices. One device shows this, the other device shows that. Why? Because these are not identical. These are not natural. These are not atoms. These are fabricated devices. So they're different. And in particular, if there is a huge frequency mismatch, the light is completely scattered back, and you don't get anything at that frequency. So that's a generic problem. So we have a hammer, and that's a topological hammer, and let's see whether it works. So this now, instead of like having one resonances, like these ones that we have over here, we have an array of resonators. So each of these ones now is composed of many modes because we have a 2-dimensional array. So imagine that we have n resonators coupled to each other. Now each line will split to n lines, and they will be described by this Hamiltonian. So now if you zoom in to each of these, each part of this band, and then look at the transmission or the delay time as a function of frequency, you see the following. What is interesting is that we repeated the experiment. Actually, Sunil, who is actually faculty in the Boston area now, what he did is that he fabricated different devices, measured the spectra, and then superposed them on top of each other. And then, not surprisingly, if the photon goes through the bulk, if the photon is resonant to go through the bulk, it changes from one chip to another chip. But if the photon is coming and you're sending it at the frequency that corresponds to the edge band, then you see from chip to chip it doesn't change. So this is the statistical manifestation of that robustness that I showed the imaging for. The imaging was just it's nice, but in the end, in reality, you have to show that when you do it many times over hundreds of devices, we saw that actually topological protection exists in a photonic system, and that's that. Okay? So now we have that not only for this mode, but for this mode, that corresponds to many of them. So we pump one of them, and then we generate signal-on-idler in the other one. So we use these robust channels, these robust edge states at different frequencies to generate photons. Okay? So we use it as a way to do this robust phase matching. So this is the experiment. This is the one-dimensional system. If you pump it over here, you generate signal-on-idler, and then in 1D, it changes from device to device. These are 3 typical devices. If you do it in 2D, then you would see that the photons are predominantly coming at the band that you have engineered the system at. So this is the experimental work. So it has all kinds of disorder. The frequency mismatch is actually as much as the tunneling between the resonators. The magnetic field is fake. It actually changes from side to side. It's not a uniform magnetic field that we have applied with a magnet. Nevertheless, it actually works. And then you can show that they are actually truly single photon, pairs of photons. So if you herald on detection of one of them, if you look at the other channel, it's a single photon, and that's a photon correlation function measurement. So, okay, so that was just to generate pairs of photons. Can we do something more, even something more maybe useful? And that's the topic of optical frequency comb. So frequency combs, you can think of them as meters, measuring tapes for time and frequency. So in a measuring tape, you have these ticks that are distance at the fixed value. They are equidistant ticks. These are equidistant ticks in time or frequency. So these are peaks that are equidistant in frequency. You take the Fourier transform. If these modes are locked, they're not independent, then the Fourier transform will give you this, vice versa. So the way that they're generated is that you have a nonlinear material. You shine some CW continuous wave laser at the fixed frequency, and then you generate these combs. And they're useful, you can imagine, for all kinds of things. Once you have a measuring tool, you create new science. Like that's the most fundamental as it gets. So there is a whole effort to miniaturize it, not to make it on this tabletop. That was actually the subject of this Nobel Prize. Can you miniaturize it? And this is a very nice review by Tobias Kippenberg and company, that if you have a ring resonator, you pump it at this frequency, you generate this comb. But unfortunately, most of this comb most of this pump is not converted to the comb. Most of it just comes unimpeded, which is one of the issues. But there are other issues. These combs don't have any feature. They're just equidistant peaks. Can we have actually more features to them for example, spectroscopy? So there are a bunch of challenges, and there are ways to address them and a lot of people are thinking about it. Again, we have our topological hammer, and we want to see whether we can solve this problem. Okay. So the way that you can think of frequency comb is actually the same Hamiltonian that I showed for the pair generation. You just pump it harder. So how does it work? You pump over here, you generate photon signal on idler at higher frequency and lower frequency, but you keep increasing your power, and then you generate more bands, and then these mini bands also generate more bands, etc. And in some particular values, the gain and the dispersion will conspire such that the photons would come at the same at frequencies that are equidistant from each other. So why I say this is that if you have nonlinearity in a system, your frequency shifts. This is Kerr nonlinearity, N2 times I. So if you put more power, the frequency would shift forward or backward, depends on the sign of the N2. But you have also some dispersion in the system, so higher frequencies are walked off forward or backward. And in some regimes, they compensate each other, such that you will have this nice frequency coming out. And what we would like to see is that whether the topology that we realize can lead to robust phase matching can play a role over here. So in a single ring resonator, what's happened, how a frequency comb is generated, is very simple. These are these different modes correspond to different shapes over here. You pump it at one frequency, and then you tune the frequency, and then you see the power changes like this. So at some specific frequency, you have this soliton. So this is in time. It goes around the system. Each round trip, it will finish a circulation. In frequency, it's like that. Most of it comes out at the pump frequency, but then you have all these peaks that are coming at all the other frequency. This is the one that you like. If you go at a different frequency, then you see just some chaotic, random features. If you go at other frequencies, then you see something like this, that this is like a soliton, but it's a bunch of them that have created a pattern. They're called Turing rules or Turing pattern because Turing, the famous Turing, came up with this idea: if you have a nonlinear equation that has also dispersion, the nonlinearity and dispersion can compensate each other and then lead to emergent periodicity, in particular in biological systems like a zebra. And like why that you have stripes and some shapes emergent in a biological system. I'm not an expert to what extent this is actually true, but these are called Turing patterns for this reason. So they are called Turing patterns. This conversion efficiency is low. Yes?
Okay, so you said we can interrupt you. So
Yes, please, please.
So take the wild card.
Yes.
So a lot of times for Turing patterns, right, you have some sort of attractive and repulsive force that are kind of fighting against
Yes.
each other. So what would those?
Very good question. So this was the one that I briefly mentioned over here. So this gain and dispersion. So when you imagine that you put more power in the system and you accumulate more phase because your kernel linearity, more power, the index of refraction, the effective index of refraction, let's say, increases. Okay, so it means that these modes will shift to the forward, to the higher frequencies. But then you have to have some dispersion such that they would shift them backward. So meaning that higher resonant modes would have lower frequencies. So instead of being, if your system does not have any dispersion, and then if you have a system like this, just a linear waveguide, the modes of the system would be equidistant from each other. This is like what Boubacar showed. Like you have a linear dispersive material, and then these modes will be separated from each other like that, right? Now, if you have a group velocity dispersion, they would be a walk-off instead of like that. Now, you also have nonlinearity, and they would kind of bring them back. Or if they're this way, they will push them. So these two are competing with each other. So this is the group velocity dispersion. That this is this term. So you have omega is equal to ck, but then you can have higher orders. So I'm talking about this one. Sounds good? Yeah. Yeah. Maybe I answer it differently. So when you generate these peaks, at different frequencies, they can be locked or they cannot be locked. If they are locked, because I can have a bunch of peaks at different frequencies that they don't talk to each other. This is the unlocked version. This is called the noisy comb version. If you take their Fourier transform, you don't get this. The different frequencies have to be locked such that when I take their Fourier transform, they give me this. So the soliton is actually a very pure situation that when you take its Fourier transform and then looking at in the time domain, is just the peak that is oscillating like that. But over here, they're not locked. They would still sometimes produce noisy comb, sometimes produce nothing, and then come out. And then over here, there is another way of locking them. So I hope that kind of answered the question. So in the topological one would be just the same. Now we have the same slide that I showed you, but now instead of one peak, one resonance, we have many resonances because we have an array. And then if you pump it at the specific frequency, that I don't go into the details, you will get not only just these peaks that are circulating at a very fast time scale, that L over C, but also there is a structure, there is a kind of a nested structure or supersoliton structure that goes around the system. So each resonator would have a soliton, but then they are locked to each other and then create a supersoliton. So that's why it has a nested form. So in the frequency domain, that was in the time domain. In the frequency domain, not only you would see these peaks, but also this like kind of nested peaks around it. If we also look at this conversion efficiency, just numerically, this is a numerical paper that's in this noisy projector, that you get 50% efficiency, just based on our numerics. And it's robust against disorder. We can actually remove one of these resonators in our numerics and then see it doesn't really care about the presence or absence of that resonator. So what that leaves us is with a phase diagram. So you have a phase diagram of frequency and amplitude of the incoming pump. For this region, you will see this supersoliton creation. For big region, you see chaos, and then these solitons, these Turing rolls. And right now, we are at just this numerical model. We don't have a phenomenological model. We don't have like a topological quantum field theory like in electronic system to understand phenomenologically when you have a bulk, you have a corresponding edge, etc. And also the experimental implementation, which I will talk about, which took us almost 4 years to implement it, basically. So the lead graduate student is Chris Flower, who really pushed this through for many years, different platforms, different material, fabrications, etc. And it's a big collaboration with our colleagues at both Maryland and NIST. So it's in press, it's coming out, but you can read it. It's on the archive. It's not in New York Times. It's not going to be in Washington Post either. In some journal. So this is using now silicon nitride platform, and the typical numbers are here. We are operating at telecom, 1550 nanometer. Waveguide thickness is 800 nanometer. The typical length of this resonator is about 20 micron, and we are dealing with hundreds of resonators coupled to each other. Usually, making these hundreds of resonators to nonlinearly couple to each other is a very, very challenging task. But it seems that topology is actually helping us to do that. You can look at just the linear response of the system. You have these small features that repeat each other after each free spectral range. So this is the free spectral range is this C over L, 6 nanometer, and then these mini features. If you zoom in, you have the bulk response, you have the bulk response, and then you have the edge response. If you move into the edge response, you will see these tiny peaks that they are correspond to these super modes, not the mode in each resonator, the mode in this larger resonator. So they're larger, so their frequency, the corresponding frequency or wavelength is smaller. So these are these tiny ones. What is important is if you look at the group delay, in the bulk, it's all over the place, and the other bulk is all over the place. But in the edge band, in between these magnetic bands, you see that it's flat, and that's the one that we would like to use. So now if we pump the system and increase the power, you see that little by little, the comb is generated. And then you have these very nice peaks that are coming out distanced by the free spectral range. So we actually had that, and then we send it for the review, and then we claim that, well, not only you have these peaks, but you have also these nested ones that you see a little bit over here. Now with the light, it's even harder to see. So, and of course, the referee said, well, we can hardly see it, even with the lights off. So you should convince ourselves, convince us that this is actually the case. We didn't have any spectrometer at that limit, but while the paper was under review, my postdoc found a company that they have come up with a new way of measuring it. Again, a new measuring tool is amazing. So we just got a demo, and then using that demo, we could manage to resolve them. And this is it. So if you go now to individual ones, you can really see that these are distant peaks. It's not just those little things in the previous one. So this is our result. If you tune the frequency in other regimes, you don't see them. You see some structure. For a single ring, you certainly don't have that nested structure because it's just one parameter. I ask AI, what is a nested frequency comb? This is what is coming out. And I said, in the absence of nested teeth, and this is it. in the wild dream. Actually, I like this cool piano. Has a meaning of frequency in it. But okay. We can also image them. So we can filter the pump and then see what are the generated frequency comb. You can see that the edge ones are predominantly confined at the edge. And if you pump the bulk, you will see that it's predominantly in the bulk. We don't call them chaotic because they have some structure. There might be some limit cycles, etc. There are many interesting theoretical questions that are still open. And I would like to say that linear topology is very well understood. Many-body topology is also very understood with TQFT for, in particular, quantum many-body systems. But in between, the nonlinear one is not understood. We don't even have like a formalism and a theory to understand it. So it's an open theoretical question. So I think I should wrap up, right? I had 40 minutes or 45 minutes.
Yeah, take another 10.
10 minutes, very good. Okay. So I just talked about the photon pair generation, which was over here, and then the solitons. And another direction is to now integrate it with two-level systems that can strongly couple to these edge states and moving forward. And what is important about this topological photonic crystals, that topological photonic crystals were around for a long time. And you have a periodic structure. You solve your Maxwell's equation, and then you get a band structure. In the Brillouin zone, you have energy as a function of momentum. What we didn't know that apart from this just frequency as a function of momentum, there is also the way that the wave function changes over the Brillouin zone matters, basically the topological part of it for the photonics. And this kind of, that's part of another topological photonics now in crystalline structure. So if you put two systems that have two different topology, and then you squeeze one on the other, and inspired again by topological insulators, you can create a topologically non-trivial system on this side and on this side. And if you interface them, you will have an edge states in between them. The time reversal symmetry is not broken, so you will have one polarization going this way and the opposite polarization going that way. So Maxwell's time reversal is preserved. And then what we showed is that if you have a two-level system over here that can emit light with specific polarization, if it's sigma plus, it will go over here. And if it's over here, if it's sigma minus, it will go over there. That I won't go into the details of that. Instead, I would like to highlight where we are going a little bit away from this into the many-body case, and also another direction where this is an interplay between electrons and photons. So far, we just talked about topological photonics inspired by electronics, but we can actually put them together. And then how to measure this many-body Chern numbers or fractional statistics of this system. So I will be very, very brief and high level. Just want to motivate how this is done. As I said, in many of our condensed matter measurement is based on linear response paradigm. That we send something either DC or AC, and then we look at the response of the system. But what we have with this quantum simulator, regardless of their flavor, either they're ions or Rydberg or superconducting qubit, you have more freedom. So sometimes you have less freedom from some part. For example, you may not even apply linear response to them because they're fundamentally different. Sometimes they're bosonic degree of freedom. Sometimes it's technical. There is a lack of suitable disorder or the scale of the system. But then what is interesting is you have access to the wave function. You can measure all kinds of correlators that you could not measure in your wildest dream in a condensed matter system. So many of these measurements are based on ancilla. So you have one ancilla that you couple to the system, to your many-body system. You do some kind of interferometry, Ramsey interferometry, who used to be here. And depending on how you set it up, you can measure the properties of the Hamiltonian that you're integrating or the properties of the wave function that you're integrating. So you can, these are just a few examples that I was involved in parts of them. You can measure even fractional statistics, you can measure out of time order correlator, but these are all based on having one qubit coupled to a many-body system. It would be nice to come up with ways that are not based on that. These are not ancilla-based, and you just want to have your system, and then you just do many measurements and extract the fractional the fractional statistics or topological invariance in this system. In particular, you imagine that you're not allowed to put the system on a cylinder or on a torus, etc. It's on a disk. How you would go about that? So this was a work that we did a few years ago in collaboration with my colleague Meysam Barkeshli and Peter Zoller's group, and the basic idea was that even if you don't have access to this torus or cylinder, etc., you can simulate them using measurement. So the measurement, in particular, the swap measurement, and I won't go into the details of it. If you're interested, we can chat afterwards. Is that this partial swap measurements can simulate creating a handle in the system, and then by doing so, you can actually have your desired topology, and then you can do your measurements out of it. So with that, I just highlight what I wanted to say about this correlated system, and I finish. The new axis that we are interested to look at. I showed you two axes, photon-photon interaction and photon number, but we believe that there is a new axis, and that's the correlation between electrons. Usually we thought about a light-matter interaction in terms of two-level systems, either being an atom, a quantum dot, the NV centers in diamond, etc. But in a material, the electrons are itinerant. The electrons can move around and then can also interact with your light. So you can have a Mott insulating state fractional quantum Hall to interact with your electrons. So what kind of new regimes of quantum optics you can envisage? And this is like a cartoon of a bunch of things that we thought with our colleagues, that you can think of like a fractional quantum Hall states in an optical cavity. We can think, so this is like not driven. There is no photons in the system, but they are in a cavity and the matter is strongly interacting. Or you can not put the system in a cavity. You can strongly drive it with a lot of photons, and then you can ask whether you can have driven superconductivity, etc. So this is a new topic, and we have just started to look into this, but in the interest of time, I'll just stop at this point, and thanks for your attention. I think the microphone, yeah.
Hello, Alejandra Ponte again here. I wanted to ask you, you made an emphasis of making sure that whenever we create a new measurement device, it allows us to explore new types of physics. Now, atomic clocks are obviously not a new measurement device, and given that you have some relation with NIST, although not the NIST in Colorado Boulder who's working on atomic clocks, I would like to ask you, how do you think these new types of frequency combs could help advance that type of atomic clock that we're currently working on? We hadn't seen much improvement until Dr. Anna Maria Ray recently posted, submitted her results, and she made quite advancements in atomic clocks. But the general structure of atomic clocks hasn't changed, and certainly not the frequency comb that is used in them. Do you think this new types of frequency combs have the ability to push atomic clock technology further?
The answer is that I don't know. Like a short answer, because until like a few months ago, we were not even sure we can create these nested combs. So we're not thinking like really deeply about it. Certainly they have these new features, and certainly I can talk about spectroscopy, because that we think that there is a merit to that. Imagine that you have different lines that are separated from each other, but then you want to have a very high resolution around each line, but you don't want to have a comb that is finely teeth all the way from one line to another line, which means that you have to put a lot of power in this comb. So certainly these kind of structured combs are useful for that. But for the case of the clock, I don't know. Like maybe for locking into different frequencies, etc., because now you have like different scales in the system, it would be useful. But I don't have a concrete answer for that.
No, thank you. I just needed the insight into it is what I was looking into.
That's
So
right.
that's a very
The
great answer.
structure,
Thank you.
the structure,
Yeah.
you have like in particular, just to give an example, is like 2 gigahertz over here and then 700 gigahertz in between them. It's just like 2 different scales.
Wonderful
This-
talk.
this
Thank you
one.
so much.
Yeah.
Hi, Eddie. Thanks for the talk. From a materials perspective, could you emphasize the current state? Because you mentioned quantum dots and other 2D materials. So you could just highlight the current state for device fabrication now, and then where you think it might be heading.
For these ones, for this topic.
Yeah.
A very, very good question. So we are working with 2D material in particular because they're new. We can play with them. They have many interesting features. In particular, these van der Waals materials like transition metal dichalcogenide, etc. Because a lot of work is being done on them. We understand them. They have this superlattice structure. We have been able to see like strong exciton-exciton interaction with them, which was not possible with gallium arsenide, that people have actually did in exciton-polariton context. So we would like to kind of explore just so far in our lab, just the TMDs, but some of this is kind of agnostic to the material itself. We've been even thinking about cuprates, going back and then see what kind of light manipulation you can apply on cuprates and other correlated material.
Okay, thanks.
But the focus right now is TMDs because they're really cool. You can be stacked and have all kinds of. I think Pablo, I already talked, Pablo
yes,
already gave a talk. So they're cool. And what we are looking at, we're not looking at graphene because graphene doesn't have a band gap. We are optical, so optical you really need to be in the semiconductor. So that's why we're using transition metal dichalcogenides.
Yeah, Mohammed, I was going to suggest that the other thing you may want to look is with the work that Marco and his folks have been doing integrated photonic structures in lithium niobate, because you have the ability to have something that's active.
Yes, unfortunately, I didn't have that slide. So we had this silicon nitride platform, but we looked into lithium niobate with our collaborators. The fabrication didn't work out, but there is no fundamental reason why we can't do it in lithium niobate, and there is this very nice opportunity to modulate individual sites, and even related to the topic tomorrow, what Dirk is going to talk about. For integrated photonic circuits. Yeah.
So why don't we're going to break the session there and have our coffee break. I was going to have you come back. What we'll do is we'll start the next session at 11:15. So I'll give you your 15 minutes back. So we'll start the second session a little bit late, the sensing session. Cool. Just thank our speakers from this morning again.